Okay, at last I get to simple linear regression. And of course, I'm sure you've all watched the video on linear correlation, right? Right. Well, anyway, I'm going to assume at the beginning of this video that you understand at least a little bit about linear correlation. If not, go find that video on understanding linear correlation. And here's the scatter plot of the example that I used in that video. And we're going to use the same example for this one on linear regression. And we're only going to deal with simple linear regression in this video in order to keep the video reasonably short, because there's a lot of concepts in regression. We're not going to get to even a tenth of the concepts that are in regression. I'm just going to try to keep it as simple as possible and just the minimum that you need to get started on regression. And then we'll do future videos on things like goodness of fit and what have you. All right, so let's continue on here. All right, so what is regression? Well, regression is a way to predict one variable from another variable when those two variables are related to each other, or in other words, correlated. The first thing to remember is that if we just want to predict one variable, and all we had was one variable, and we want to predict future observations on that one variable, our best guess about future observations is going to be the population mean. So we would just guess the mean, right? Now, we usually don't know the population mean, so we estimate it with a sample mean, right? That's a sample statistic, the sample mean. Remember that a sample is just a subset of a population, and a sample statistic, like the mean, is just an estimate of the corresponding characteristic of the population, which we call a population parameter. Anyway, the mean is our best guess because it's the only point that's guaranteed to give zero net error, meaning that if we use it as a prediction, we're just as likely to get an overestimate as an underestimate, and by the same magnitude on average, or in the long run. So of course there will be error in our prediction, but there will be zero net error. Another way of saying that is it's an unbiased predictor. All right. So there's still error in our prediction, of course. If we use the mean, we measure that error with our measures of variability, or spread. Measures like the sums of squares, the variance, and the standard deviation. Another one called the standard error of the mean, which I'll talk about at some point in a future video. But what if we want to predict one variable and we knew that that variable that we wanted to predict was related to another variable that we could also know, or that we could also measure? In our example, maybe we want to predict how many months a person has owned their current car, and we know that that's related to income. How do we know that? Well, because you've all watched the video on linear correlation, you'll remember this, right? Now, if you didn't see that video, this is really not as terrible as it looks. In that video, we went step by step through all of these calculations and figured out the correlation between income and months of car ownership, which turned out to be negative 0.74. The negative meant that as income went up, months of car ownership went down, or in other words, people with higher incomes had more recently purchased their current car. Maybe they didn't hang on to the cars for as long as people with lower incomes. Who knows why? All we know is that these variables are related. We don't know what causes what when all we have is correlational data. I've had my current car for 11 years, so enough said. Anyway, this is where we'll pick up the story. So I might think that I could use what I know about income and months of ownership to predict months of ownership from income. It looks like I could just adjust my prediction down as income increases, but by how much? Well, one way of figuring that out is by fitting a line. Remember lines from your old high school geometry class? I'm sure you remember lines. Here's the equation of a line. You might remember it as y equals mx plus b from your geometry class, but in statistics, they like to use different symbols to avoid any unseemly associations with mathematics. So in this version, b is the slope and a is the y-intercept. And you can also switch around the a and b terms like this, so it's still just exactly the same equation. We've just flipped a and b, or a and the bx around, right? See, same thing. Bx plus a is equal to a plus bx. And why do we want to do that? Why do we care? Well, it's because it's going to be more convenient when we introduce multiple regression to have that y-intercept first, and then just string out a whole bunch of different slope terms after this for our multiple predictors. Anyway, that's the first thing. That first thing there, the y with an apostrophe, we say y prime. That symbolizes the predicted value. So this is the predicted value of this equation for a line. That's what the value we would predict would be for each one of these values of the x variable, in our case income. Now, statisticians also sometimes use a little caret over the y to symbolize predicted value, like that, and they just call it y hat. Y hat means the same thing as y prime, and it is just another way of symbolizing the predicted value. And of course, we do that because we can't just stick to one symbol for anything. Everything's got to have at least 2 symbols and at least 2 names, usually 4 or 5 names. That way we can maximize confusion as you're trying to learn this stuff. Anyway, we can use a line, but which line? I mean, that line right there looks pretty good. So this one is okay, but what about this one? Or maybe this one? Oh, well, what I want, of course, is the one that gives me the best possible prediction, or in other words, the prediction with the least error. So now, just like the mean, the regression is going to give me 0 net error. But it turns out that lots of lines give 0 net error. So we have to minimize the squared errors instead. Kind of like we had to square the deviations about the mean, because the deviations about the mean always added up to 0. Same problem here. So we're going to have to square the errors and add those up, and then come up with a line that minimizes that sum of squared errors. So they call it the least squares criterion for finding the best regression line. And it turns out that the equation that will do that will minimize squared errors between the predicted values and the observed values, or the actual measured values, can be calculated with these equations for the intercept and the slope. Now, don't look away. I know you're seeing equations now. Don't look away. I'm going to hold your hand through it. We're going to go through each of these equations step by step and figure out what everything in there is. It's actually not going to be as foreign as it looks. It's not going to be as complicated as it looks, because actually, if you've done that correlation example in our correlation video, we already have all of this information that we need to just fill these equations in. So we don't even have to do hardly any new calculations. We just have to plug in values for all of this stuff from that correlation example, and we'll get our values for the slope and y-intercept of the best fitting least squares regression line. All right, but let's just go through piece by piece. So the slope, represented again by the letter B, has to be calculated first because it's going to be used, as you see here, in the calculation for A, the y-intercept. So we need to calculate it before we calculate A. Okay, and it is just the correlation times the ratio of the standard deviation of the y variable, or the criterion variable, or the outcome variable. That's the thing that you want to predict. And the standard, did I say standard deviation, or what did I say there? Standard deviation of y. And the standard deviation of x, the variable that we're using to predict y. Usually called the predictor variable, sometimes called an independent variable, although independent, I'm a little sketchy on that terminology, because independent really implies that we have a true experiment and that we've manipulated that variable, and so this might be an independent variable, but I think predictor is a more general term that does not imply that this variable is actually independent of all other variables. All right, so in our example, months of car ownership would be y, and income would be x. So where do we get the information that we need to fill in this equation? Well, that brings us back to this slide. Remember, this again is from the correlation video. This is the hand computations for calculating the correlation between income and months of car ownership. And notice that we've already calculated pretty much everything we need, right? We calculated R. That's one of the things that we need in that equation. And we've calculated the standard deviation of the y variable and the standard deviation of the x variable. There's, oh, I just pointed it out this way too. So here's R, standard deviation of Y, standard deviation of X. And so here it is, filled in. We just have to plug and chug then with a hand calculator to get out our answer. And it turns out the slope is negative 0.6. All right, once we have the slope, we just need to get the means and fill in the equation for the intercept. So going back to our monster hand computation slide, there are those two means that we need. X bar, the mean of the X variable, which was income in this case, and Y bar, the mean of the Y variable, which was months of car ownership in this case. Then we plug those into the equation for the y-intercept, and here it is. And don't forget that according to our equation, we're subtracting b times x bar. And so we're subtracting what was already a negative, because that was a negative correlation. So in other words, we're adding. And so here's our regression equation again. And now I can fill in the estimates of the slope and the intercept. And also note that I am adding the subscripts I to refer to specific observations. And here is then our regression equation. All right, so we're ready to take this regression model out for a spin. Let's make some predictions. What number of months do we predict for x sub 1, the person who has $20,000 a year in income? Well, for x sub I, we just substitute 20, and out pops our prediction, 36. So we would predict 36 months of car ownership for someone who had $20,000 a year in income. And if we do that for the rest of the observations, we get a prediction for everybody, right? And then we can look at our original scatter plot along with the predictions thrown in, and we can see that our predictions are not bad. They overpredict and underpredict in exactly the same amount, so that the net error is 0, just as it was with the mean. And statisticians have also proven that the squared error is the least it can possibly be, which is a nice feature if you want to really use regression to predict things. And typically, of course, we don't usually show the predicted values. We show the line that's defined by our regression model. And so there is the line. That is our regression line, the line that we would use to make predictions. All right, so this has gone on long enough, I think. Just a couple of take-home points. Simple regression, which is what we've covered here, means one predictor variable and one criterion variable. The predictor variable is the thing that you're using to predict the criterion. The criterion variable is the one that you want to get a prediction for. Regression can be used with either correlational or experimental data. It's often just associated with correlational data in correlational studies like surveys and that sort of thing. But it can be used, and it can be very useful in true experiments as well. All right, so I think we'll just stop it there, and we'll deal with the millions of other details about regression in future videos.